Is it not working?
No. I just remembered to start recording. So this is Gili Golan talking on maximal subgroup of Thompson group F.
Thank you. Okay, so we will talk about maximal subgroups of Thompson group F. So to those of you who are not familiar with Thompson group, it is a group which comes up in many different areas of mathematics. I think perhaps the most recent result of this type is a result of von Jones, which connects F with knot theory. So von Jones showed that every link and knot can be, that elements of Thompson group F encode all links and knots in a similar way to the way that they are encoded by braid groups. And so Thompson group F comes up in many different areas. It also has more than one definition, but the one we are mostly going to use is the one in terms of diagram groups. So every element of Thompson group F is just a diagram. Okay, it has one top edge and one bottom edge, and it is tessellated by cells, and we have cells of two different types. So positive cells have one top edge and two bottom edges, and negative cells are just the reflection of positive cells, like that. So we can have a diagram looking like that, right? We can have a cell here like that, and another one, and a negative cell, and another negative cell, and this is a diagram. This is an element of F, okay? Now, if a diagram contains a dipole, okay, so a dipole is just a subdiagram where we have a positive cell on top of a negative one, then one can reduce the dipole, replace it just by one edge, and the resulting diagram is considered equivalent to the original one. And similarly, you can have a dipole like that, so you can have a negative cell on top of a positive one, and again, you can also reduce it, you can replace it just by a pair of two edges, okay? So every diagram in F is equivalent to a unique reduced diagram. So elements of F are just reduced diagrams, I mean diagrams with no dipoles. And to define the product in F, let's say that we have another diagram, okay, another reduced diagram. Then let's say we have this diagram. Then the product of this diagram by that diagram, all we have to do is just identify, like glue the bottom edge of this diagram with the top edge of this diagram. And so we get a larger diagram. And then all we have to do is reduce dipoles. So for example, these two cells here are going to cancel, okay? So once we have a reduced diagram, there is always going to be this horizontal path which passes through all the vertices in the diagram, and such that every cell above it is positive and every cell below it is negative. So if we put vertices in the middle of every edge like that and draw edges, then we get a finite binary tree. And if we do the same at the bottom part of the diagram, we also get a finite binary tree, only drawn upside down, okay? So elements of Thompson group F can just be described as pairs of finite binary trees with the same number of leaves. Now, instead of drawing the trees, it is often easier to just list their branches. So what do I mean by that? Let me label every left edge here by 0 and every right edge here by 1, like that. So to describe this pair of trees, I can say that we have the branch 0, 0. Okay, I say that it goes to the branch 0 here. And then the branch 0, 1 goes to the branch 1, 0, right here. And then the branch 1 goes to the branch 1, 1. Okay, and this is a good description of the diagram. Now, perhaps the most common description of elements of F is in terms of the action of F on the interval 0, 1. Okay, so elements of F can be viewed as homeomorphisms of the interval 0, 1. And to see the function given by this diagram, all we have to do is add points here and alphas at the end. And now every number in the interval 0, 1 can be written in binary form as point omega, where omega is an infinite binary word. So this function, right, if omega starts with a prefix 0, 0, then it replaces it by the prefix 0. If it starts with 0, 1, we replace it by 1, 0. And if it starts with 1, we replace it by 1, 1. Okay, and a slightly different description of the same function is if you have a finite binary tree, then it gives you a dyadic subdivision of the interval. Okay, so, sorry. So here, if you start with the interval 0, 1, then you divide it in 2, then you get the interval 0, 1 over 2, and 1 over 2, 1. And you divide this interval in 2, so you get 0, 1 over 4, and 1 over 4. Yes?
Try to finish the tune.
And 1 over 4, 1 over 2. So if we do the same in this tree, then right, we can do the same in this tree. And this element of Thomson group F is just a piecewise linear homeomorphism of the interval 0, 1, which maps this interval linearly onto the first interval here, the second interval here linearly onto the second one here, and the third one linearly onto the third one. Okay, so Thomson group F is just a group of all piecewise linear homeomorphisms of the interval 0, 1, where all breakpoints are finite dyadic. Okay, so here we have 1 over 4 and 1 over 2, and all slopes are integer powers of 2. Okay, so I should also say that Thomson group F is 2 generated. So the generators look like that. They're usually denoted x0 and x1. x0 is the following diagram, and x1 is, well, the following diagram. Okay, so we are interested in maximal subgroups of F, and let me give you a brief history of the subject. Okay, so first of all, maybe I should mention that the Abelianization of F is just z squared, and the derived subgroup of F is infinite and simple. So in fact, any finite index subgroup of F contains a derived subgroup. So in other words, there is a one-to-one correspondence between finite index subgroups of F and finite index subgroups of Z squared. So when I talk about maximal subgroups, I'm only interested in maximal subgroups of infinite index because the finite index subgroups are very easy to understand, okay? So the first result is due to Savchuk from 2011. I think it was only published in 2015, but in any case, Savchuk said, if we think of F as a group of homeomorphisms of the interval 0, 1, then for any number alpha that we take in the open interval 0, 1, we can look at the stabilizer of alpha. Okay, we can look at the stabilizer of alpha, which is just a group of all, the subgroup of all elements in F, which fix alpha. And Savchuk proved that this is going to be a maximal subgroup of F. Okay, so this is a maximal subgroup of infinite index. And Savchuk also asked whether these are all the maximal subgroups of infinite index of F. Okay, so question, does F have other maximal subgroups of infinite index? And Sapir and I have given an answer to that back in 2015, but before I give you the answer, I should also say that we have also studied these subgroups stabilizers of alpha, studied by Savchuk, and in principle, right, we have the stabilizers of every number in 0, 1, so we have continuum many different subgroups, but it turns out that up to isomorphism, there are only 3 classes of isomorphism, 3 isomorphism classes of groups here. Okay, so it turns out that the isomorphism class of the stabilizer of alpha sorry, my pen is having some trouble. So the isomorphism class of the stabilizer of alpha, it has 3 isomorphism classes, and they depend only on the type of alpha. So the only thing that matters is whether alpha is dyadic or rational but non-dyadic or irrational. Okay. Okay, so that actually makes Savchuk's question even more interesting because, or irrational. Never mind. So the other option is alpha being irrational. Okay, so that actually makes Savchuk's question even more interesting because up to isomorphism, we only have 3 different maximal subgroups of Thomson group F, okay? However, it turns out that the answer to Savchuk's question is yes, okay? So in fact, F has many other maximal subgroups of infinite index. And back in 2015, we gave 2 different answers to this question. So the first solution was an explicit solution. Okay, so we have basically constructed a specific maximal subgroup of Thomson group F. Okay, now the construction itself the proof was very, very technical, but the interesting thing is that this maximal subgroup was in fact isomorphic to F3, which is the brother group of F that is defined exactly the same, only it is piecewise linear homeomorphisms of the interval where all breakpoints are finite periodic and all slopes are integer powers of 3. Okay. And the construction itself, we used, in fact, F3 is isomorphic to a subgroup which, defined by von Jones, which is usually denoted like that. And it's sometimes called the directed Thomson group F. So von Jones, in his study of the connection between Thomson group F and knots and links, he defined a subgroup which encodes all oriented links and knots. Okay, so we have used this subgroup to construct an isomorphic subgroup, which is maximal. Okay, and this is also isomorphic to F3. Okay, so, but here again, the proof is very, very technical. So perhaps a more interesting result is the implicit solution. And the idea here was actually fairly simple. Okay, so let's say, assume that you have a subgroup of F, right? Let H be a subgroup of F, such that, assume that H satisfies 3 conditions. Okay, so first of all, assume that H doesn't fix any number. Okay, so H does not fix any number alpha in the interval 0, 1. And secondly, assume that H is not contained in any proper, H is not contained in any proper finite index subgroup of F. And finally, assume also that H itself is a proper subgroup of F. Okay? Then, if you have such a subgroup, then because F is finitely generated, if you take any proper subgroup, then we know that by Zorn's lemma, H has to be contained inside some maximal subgroup of F. Okay? But if H satisfies these 3 conditions, then the maximal subgroup M cannot fix any number in the interval 0, 1. So it is not one of Savchuk's subgroups. It is not a stabilizer of any alpha. And M itself cannot be a finite index subgroup of F. Okay, so if you, okay, so you get that M is a maximal subgroup of infinite index, which is not one of Savchuk's subgroups. Okay. So to finish the implicit solution, all we had to do was just find a subgroup H which satisfies all of these properties. Okay. And
can I ask a question?
Yeah, yeah.
So when you say maximal subgroup, you actually mean not even up to a finite index. So even in the previous examples, they are not containing any finite index subgroup.
Right, they are not correct. I mean maximal. Okay, if you add any element to it, the group generator is the entire group. Okay. Okay, so the only thing left to do to finish this implicit solution is just to find an example, right, of a subgroup H which satisfies these 3 properties. And here, the main difficulty was basically in making sure that the third condition is satisfied. Okay, so generally speaking, if I give you any finite set of elements in F, and let's take H to be the group generated by this finite set of elements, then it's very easy to check whether H fixes some number, whether H doesn't fix any number in the interval 0, 1. And it is very easy to check if H is contained in any finite index subgroup of F. You just look at the image in the Abelianization, and you have to check whether the image is onto or not. And the only difficulty, generally speaking, is in checking whether the third condition is satisfied. Okay, is in checking whether H is a proper subgroup of F. Okay, so that brought us to the problem, okay, sometimes known as the generation problem. So the generation problem for Thomson group F, or more generally for a subgroup, right, for a finitely generated subgroup, is if you take a finite subset of elements, let's say in F, okay, finite subset, we want to be able to determine, we want there to be an algorithm that determines whether the group generated by X is the entire group F, okay? So we want to be able to determine whether it's true or not. So for the rest of this talk, I'm mostly going to give a solution, okay, to explain how to solve this generation problem, to give an algorithm that, given a finite subset X of F, determines whether the group it generates is equal to F. Now, this is not actually necessary to finish this implicit solution. If you're just interested in finding one example of a subgroup H of F which satisfies these three conditions, then you can do something much more simple. But we will see that the solution of the generation problem and the techniques involved actually give us some information about all maximal subgroups of F and some very interesting information about maximal subgroups, okay? So before we talk about the generation problem in F, let us consider very briefly the same problem, but for free groups, okay? So for free groups, let's take the free group F2 generated by A and B. And let's say for simplicity that I take just two elements, G and H in F2, and I want to decide whether the elements G and H generate the entire group F2. Okay, so there is an algorithm for that. Okay, there is more than one algorithm, but there is an algorithm for that due to Stallings, which says the following. Okay, so if you have two elements, G and H in F2, what you do is you start with a bouquet of two circles, and you label the first one by the word G. Right? G is a word in the alphabet A, B, and their inverses, right? So we might have something like that. And you label the second circle by the word H. And then you think of it as an automaton with this vertex as an input-output vertex. So this automaton accepts the word G, the word H, their inverses, and any concatenation of them, okay? And then what you do is you apply Stallings foldings. So whenever you have a vertex with two outgoing edges with the same label, like that, what you want to do is you want to fold these two edges, you want to identify them to the same edge. And then once you apply all possible foldings, you get a new automaton called the Stalling score of the group generated by G and H. And what's special about this automaton is that now if I give you any reduced word, say A cubed, B inverse A, in the alphabet A, B, and their inverses, then the reduced word is going to be accepted by this automaton. In other words, it is going to be readable on this graph, starting from this vertex and going back to itself, if and only if it belongs to the subgroup generated by G and H. Okay, because the idea is that originally, right, when we had the original automaton, it accepted every product of GH and their inverses, every concatenation of them. But we wanted to accept every reduced concatenation of them. So that was exactly the goal of applying all of these foldings, right? Because here we could read G inverse H, but we had to have like A inverse A, and once we folded this edge, we don't have to read A inverse A. So applying all of these foldings ensures that the final automaton, the Stalling score, accepts the reduced word if and only if it belongs to the group generated by G and H. So in particular, the group generated by G and H is the entire group F2, if and only if the Stalling score looks like that. It is just a bouquet of two cycles. We have two circles here, one labeled A and one labeled B. Okay? So let's go back to subgroups of Thomson group F. And what we would like to do is we would like to have a singular construction. So we are going to call it the Stallings two-core of subgroups of, let's say, a subgroup H of F. And this is basically a general construction for subgroups of diagonal groups due to Guba and Sapir, but I'm only going to give it in the case of subgroups of F. So to demonstrate, let's say that H is generated just by two diagrams. Let's take delta 1 to be the following diagram. This is just x0. And let's take delta 2 to be the following diagram. So we have okay. And what we want to do is we want to have a two-dimensional analog of the Stalin score of a subgroup of a free group. So what do I mean by that? So in the case of free groups, right, we started when we had two elements. We started with a bouquet of two circles. So here we want to start with a bouquet of two spheres. So we start with two diagrams. So what we want to do is we want to identify the top and bottom edges of all of this diagram. We want to identify them to one edge. So I'm just going to label all of these edges by the same label E, so that when I label some edges by the same label, I mean that they are identified, they are the same edge. Okay, I'm not going to draw it as a bouquet of spheres, but these edges are identified. And I think of the edge E as a distinguished or an input-output edge. Okay, and then the next step is we want to apply foldings. And here we have foldings of two different types. Okay, so if we have two cells which look like that, and they share I will call it the top edge here, they share the one edge they have, then I want to fold the two cells together, and in particular identify the left bottom edge with the left one here, and the right bottom edge with the right one here. And similarly, if I have two cells which share their bottom path, okay, then what I want to do is I want to fold the cells together, identify them, and in particular identify the top edge here with the top edge here. So for example here, let's look at this picture. We have that these four cells have the same top edge E. So we have to fold all of them together, identify them. And in particular, we identify, let me label here the bottom path by F and G. Then the bottom path of this cell should also be F and G. And the bottom path of this cell should also be labeled FG. And the bottom path of this cell should also be labeled FG. Okay? And now we see that we have three cells with the same top edge G. So they all have to be identified. So in particular, the right bottom edge here is G. So the right bottom edge in all of them should be labeled G, should be identified. And let's label the left edge here by H. So the left edge in this cell should also be H. And the left cell in this edge is also H. And notice that this cell now also has top edge G. So the bottom path should also be HG. Okay. So here we have HG. And now we see that here we have again two cells with the same edge, with the same top edge H. So we have to fold them, we identify them. Let me label the bottom path here by AB, then the bottom path of this cell should also be AB. And if we look very closely, then no more foldings are applicable. So we got a two complex with a distinguished edge E, okay? And we call it the Stalin's two core of the subgroup H, generated by delta 1 and delta 2. And we think of this two complex as a two automaton, in the sense that it can accept a diagram from F or not accept it. So what do I mean by that? Let's take, for example, the following diagram. Okay, so we have, just a second. Okay, so we say that this core accepts the diagram delta if there is a homomorphism of two complexes from the diagram to the core. So I just mean a mapping which preserves adjacency of cells, adjacent vertices, such that the top and bottom edges of the diagram, both of them are mapped to the input-output edge E. Okay? So for example, here, let's check if the diagram delta is accepted by the core. So if I take, if the diagram delta is accepted by the core, then we must have a mapping that maps the top and bottom edges, both of them to E. And then in the core, there is at most one cell with a given top edge. So this cell has to be mapped to the cell, I call it E goes to FG in the core. And then this cell here has to be mapped to the cell F goes to FH. And this cell has to be mapped to the cell, here we have H goes to AB. And this cell has to be mapped to, we have B goes to BH. And again, in the core, there is at most one cell with a given top path. So the cell here, we have AB, it has to be mapped to the cell ABH. And this one has to be mapped to HGG. And then again, we have HG, this one has to be mapped to G. And finally, yes?
Give me 5 more minutes.
Oh, that's not good. Thank you. And finally, this cell has to be mapped to the cell FGE in the core. And there is such a cell, so we can complete the mapping. And so we say that the diagram delta is accepted by the core. Okay, so delta is accepted by the core. So let me very quickly say a few observations. So the first observation is that if we started with two diagrams, delta 1 and delta 2, then the diagrams delta 1 and delta 2 are going to be accepted by the core, right? You can think of it as readable on the core starting from the distinguished edge E and going back to itself. So they're going to be accepted, and also their inverses and any concatenation of them. But the goal of applying all of these foldings, just like in the case of free groups, was to guarantee that if a diagram is accepted, then the reduced diagram equivalent to it is also accepted. So it turns out that the entire group, every reduced diagram in the group generated by delta 1 and delta 2, is accepted by the core. Okay? Now, a slightly less trivial observation is that the core of H does not depend on the chosen generating set. So we really can talk about the core of H. And so we can also define the closure of H. The closure of H is just going to be the subgroup of F of all reduced diagrams accepted by H. Okay, and essentially what we have said so far, and the most important property, is that H is always contained in the closure of H. Okay, but unlike in the case of free groups, H is always contained in the closure of H, but the inclusion here is very often strict. Okay, but why is it still good for us? So the closure of H is the subgroup of F accepted by H, of all diagrams accepted by H. So for the closure of H, we have a very simple solution for the membership problem, right? If we want to decide if a diagram belongs to the closure of H, all we have to do is what we did just here. We have to check if it is accepted by the core of H. So in particular, if at least one of the generators, if x0 or x1 is not accepted by the closure of H, then the closure of H is a proper subgroup of F, and so in particular, H is also going to be a proper subgroup of F. So it gives us a partial solution to our problem. If we have a subgroup H and we manage to prove that either x0 or x1 is not contained in the closure of H, then H must be a proper subgroup of F. Now, we don't have much time, so I was going to demonstrate, but I would skip it. You can check easily here that if you take the diagram of x1, then it is not accepted by the core. So for example, in this example, just by constructing the core, we see immediately that this subgroup H is a proper subgroup of F. So we already get, in this specific case, a solution for our question. But generally speaking, there are groups, okay? There do exist groups. There exist subgroups H of F such that the closure of H is equal to F, but H is a proper subgroup of F, okay? So the main theorem is that it is true that there are groups such that the closure of H is equal to F, but H is a proper subgroup of F. But, sorry, theorem, okay? But if you do get that the closure of H is equal to F, it is still very easy to check if H is a proper subgroup of F or not. Okay, so the theorem says as follows: let H be a subgroup of F, then H is equal to F if and only if two conditions are satisfied. So the first condition is that the closure of H is equal to F, which is basically equivalent to saying that the core of the subgroup H is equal to the core of F. And the second condition is just that H is not contained in any finite index subgroup of F. Okay, so H is not contained in any finite index subgroup of F. Okay, so this gives a very simple algorithm for deciding, I will finish in a couple of minutes, for deciding if I give you finitely many elements, whether they generate the entire group or not, okay? Because to check the first condition, you just have to construct the call and see if it coincides with the call of F. And checking the second condition basically just means looking at the Abelianization. So I would write the corollary because I want to say something about maximal subgroups, okay? So a corollary of that is that if you have any maximal subgroup, okay, any maximal subgroup of F, any maximal subgroup M of F of infinite index must be closed. What do I mean by must be closed? I mean that it satisfies that the closure of M is equal to M. Okay, so this is an immediate corollary of the theorem, because if you get any maximal subgroup, okay, if the maximal subgroup weren't closed, then the closure of M would strictly contain M, and because M is a maximal subgroup, then the closure of M would be equal to F. But then if the closure of M is equal to F and M is still a strict subgroup of F, then M has to be contained in a finite index subgroup of F, which cannot be the case if M is maximal of infinite index. Okay, so the corollary from the theorem tells us that every maximal subgroup of F of infinite index is closed, which means that you can study it by means of its core. So for example, it means that the membership problem is very simple, right? If you know how to construct the core of this maximal subgroup, then if you want to check if an element belongs to this maximal subgroup, all you have to do is check if it is accepted by the core. And in fact, I don't have time to get into it, but it also gives you some other properties of the maximal subgroup, okay, of closed subgroups in general. And one last comment I would say is that using techniques for studying this core and basically, well, this kind of techniques, you can also generalize the theorem of Sapir and myself from 2015, showing that Torsion Group F has a maximal subgroup isomorphic to F3, to showing that Torsion Group F has a maximal subgroup, isomorphic to Fn for any n, not just n equals 3. Okay, so you get infinitely many non-isomorphic maximal subgroups of Torsion Group. Okay, sorry for running late. I'm done.
So I ask you to unmute to thank our speaker. Thank you, Gili. I'm not sure we have time for questions because we're trying to be quick on the schedule. Maybe if somebody has one question, then we can squeeze it.
I have a question, Gili. Do you know if these subgroups are finitely generated always?
No, actually, it's a very interesting question. I believe, well, first of all, you can have, maximal subgroups of infinite index which are not finitely generated. Right? The interesting question is if you have a finite core. So if you start with a finitely generated, essentially what we showed is if you start with a finitely generated group, then the core is also going to be finitely generated. So assuming it's not inside, not the core is going to be finitely generated, then it's going to have a finite core. So the interesting question, which is still open, is whether when you have a group with a finite core, whether it has to be finitely generated. I do not have an answer for that. I tend to believe that in the case of maximal subgroups, they have to be finitely generated, but I'm not even sure about that. So far, I haven't been able to prove it. But in several cases, like depending on the presentation of the core, then you can say very often that it is finitely generated. I don't have any example where I cannot say that, but this is an open question. Okay, but generally speaking, maximal subgroups of infinite index can definitely be infinitely generated. Even, for example, just if you take the stabilizer of any irrational function, then it's all of any irrational number, then it's already going to be infinitely generated.
Mm. Okay, I have other questions, but maybe I'll talk to you privately.
That's a good idea. Let's take a 4-minute break and before the second talk. So thank you, Gili, once again.
Thank you.
bezig zijn. Is dat niet?
Okay, these were 4 minutes.
Okay, can everyone hear me?
Yes, we hear you. Let's see if.
Yep, great.
Okay, so our second speaker is Alex Margolis from the Technion. Alex will tell us about discretizable quasi actions.
Thanks very much, and thanks to Chloe and Nir for the invitation to speak. So, brief outline of what I'm going to say. So, sample application and motivation for investigating what I call discretizable quasi actions, quasi-isometric rigidity for the class of Z biohyperbolic groups. And this is really not the main topic of the talk. It's a sample application of discretizable spaces and discretizable quasi-actions. So I'll talk about what they are and give lots of examples and say how they're related to normal and almost normal subgroups and quotient spaces. Then I'll talk about some dichotomies in the world of finitely presented groups between continuity and discreteness, And in lots of situations, for instance, for the class of hyperbolic groups, you're either a co-compact lattice in a rank 1 Lie group, or the group is discretizable. And this is very useful for proving various Qri rigidity theorems. And then I'll talk about some applications, for instance, Qi invariance of almost normal subgroups, and also understanding what possible locally compact groups a finitely generated group can embed in as a uniform lattice. Okay, so I'm interested in quasi-isometric rigidity. So the setup is, if you have a finitely generated group, you can consider its Cayley graph equipped with a natural metric in which edges have length 1. And this isn't well defined. It's only well defined up to quasi-isometry, in that if you pick 2 different generating sets, you'll get quasi-isometric Cayley graphs. And the broad question is, if you have 2 groups which have the same geometry, to what extent do they have the same algebraic properties? So here's a sample theorem, which can be deduced from work of Kapovich, Kleiner, and Lieb, and Moshe, Segev, and White, which says that if we have a finitely generated group which is quasi-isometric to Z times F2, i.e. it has the same large-scale geometry as Z times F2, then it's virtually Z times a non-abelian free group. And in general, this sort of theorem won't be true. There's no, in general, like if you have 2 direct product of 2 groups, there's no reason to expect that a group quasi-isometric to it will also split as a direct product. And this is perhaps most strikingly illustrated with the Berger-Moses groups. So these are groups which they're uniform lattices in the products of 2 trees. In particular, they're quasi-isometric to the product of 2 free groups, but they're simple. So they have no normal subgroups. They don't split as direct products or anything like that. And the broad outline of this, of how you prove this, Kapovich, Kleiner, and Lieb show that in this situation, you have a group which is quasi-isometric to Z times F2. Then you have what's called a quasi-action on F2. I'll define what a quasi-action is in a few slides. And then Moshe, Segev, and White show that you can quasi-conjugate, or you can straighten this quasi-action to a genuine isometric action on a locally finite tree. And what I'm interested in is generalizing the second step, the step of Moshe, Segev, White, to more general groups and spaces. So a Z by hyperbolic group is a finitely generated group which has a infinite cyclic normal subgroup such that the quotient is a non-elementary hyperbolic group, i.e. it's a hyperbolic group that's not finite and not virtually Z. And I prove the following theorem. If we have a finitely generated group quasi-isometric to a Z by hyperbolic group, then it's also Z by hyperbolic. And as I said, in general, these sorts of theorems aren't necessarily true. It's not true that having a normal subgroup is preserved by quasi-isometries. There's something interesting going on here. And to complement this, we have a Qri classification. 2 Z by hyperbolic groups are quasi-isometric, if and only if the associated hyperbolic quotients are quasi-isometric. This was actually already known before, so I'm more interested in the first part, the Qri rigidity. And the broad outline is the same. The first step is the same. The result of Kapovich, Kleiner, and Lieb that I alluded to on the previous slide says that if we have a group quasi-isometric to a group of the form Z by Q, then this mystery group G has a quasi-action on Q, and that leads us to the main problem of the talk. We want to understand quasi-actions on hyperbolic groups, on hyperbolic metric spaces. So I talked a bit about quasi-actions. I should now define them. So if we have a group G and a metric space X, a quasi-action of G on X is a collection of quasi-isometries of X indexed by G with uniform constants, i.e. every Fg is a Ka quasi-isometry for some uniform K and A, such that if you compose Fg with Fh, then you get FGH up to some uniform error. And also the quasi-isometry representing the identity, FE, is the identity up to some uniform error. And if we have two quasi-actions of the same group on two different metric spaces, we say the quasi-actions are quasi-conjugate if there's a quasi-isometry between the two spaces, which is coarsely equivariant, i.e. this inequality holds. And the key example, which is really what motivates the definition of a quasi-action, is that if we have a nice isometric action of a group on a metric space X, and we have a quasi-isometry from X to Y, then this quasi-isometry quasi-conjugates the isometric action to a quasi-action on Y. And to illustrate my philosophy and the sort of thing I want to do, I'm going to talk about two key examples. The fundamental group of a closed hyperbolic surface, pi1 of S, and the free group of rank 2. These are both hyperbolic groups. And I'm going to claim that pi1 of S should be thought of as a continuous or smooth object. Now, obviously, both groups are finely generated, so they're both discrete in some sense. But from the point of view of coarse geometry, we have this theorem of Tukey-Gabay and Castan-Jungreis, which says that if we have a quasi-action of any quasi-action of a group on pi1 of S, then it can be quasi-conjugated to an isometric action of the same group on the hyperbolic plane. So essentially what this says is, out of analyzing all possible quasi-actions, we start off with this discrete metric on pi1 of S, we get the nice continuous Lie group action on the hyperbolic plane. And something very different happens to the free group of rank 2. If we look at quasi-actions on the free group of rank 2, which are co-bounded, i.e. there's some bounded set, which when you translate it by G, coarsely fills the whole of F2. This is, every such quasi-action can be quasi-conjugated to an isometric action on a locally finite tree. And most people, I hope here would agree that H2 should be thought of as a continuous smooth object. It's a smooth manifold, whereas a tree is a much more combinatorial, discrete sort of object. And some more ways of illustrating this qualitative difference. The isometric group of H2 is a Lie group. It has a finite index subgroup which is connected, whereas the automorphism group of a tree with the standard topology, the compact open topology, is totally disconnected. The isometric group of H2 acts transitively on H2, which is the connected space, whereas although a tree is connected, if you look at the action, it sends vertices to vertices, and you have discrete orbits. So I'd like to think of pi1 of S as being coarsely continuous, and F2 as being coarsely discrete, or discretizable. So what I want to now do is come up with a robust definition for being coarsely discrete, give lots of examples for other groups and spaces, and then be able to prove something with it, be able to deduce some nice Qri rigidity results, and what possible groups can contain discretizable groups as uniform lattices. So for the next few slides, I'm going to assume X is a proper geodesic metric space. And this is the key definition. We say that the space X is discretizable if it satisfies one of the following equivalent conditions. One, so any co-bounded quasi-action of G on X can be quasi-conjugated to an isometric action on a locally finite graph. And if you have seen other Qri rigidity type theorems of this sort, where you quasi-conjugate quasi-actions, you might think this doesn't tell you that much, it's quite weak, because Y doesn't have nice local geometry. X might be a symmetric space, it might be a building, a cat-0 cube complex, some nice space, and you replace it with Y, which a priori is just some locally finite graph, quasi-isometric to X, and doesn't have any nice local geometry. The point of this isn't the local geometry of Y, but it's more the fact that knowing you have an isometric action on a locally finite graph tells you something interesting about the group G and the quasi-action. And that's illustrated in the second equivalent formulation, that every co-bounded quasi-action of G on X has something called a coarse stabilizer. So what's a coarse stabilizer? So if we have a quasi-action of G on X, we say some subset of the group is bounded if the quasi-orbit of the point, if one point is, then any point is bounded. So this is a fairly robust notion. Useful comparison, if the group is actually topological and acts continuously and properly on X, then this is the same as saying that a subset of the group is pre-compact. So this is somehow a generalization to the case when there's no nice topology on G necessarily. Gives us a sort of a notion of what it means for a subset of the group to be small relative to this quasi-action. And then we say that a subgroup is a coarse stabilizer of the quasi-action if the following two things hold. We want the subgroup to be bounded, so we want the orbit of the point to be bounded under this quasi-action. And then we also want every bounded subset of the group to be contained in finitely many left H cosets. So the two conditions, the first condition implies H can't be too big. And the second condition says H can't be too small. And in fact, the coarse stabilizer is unique up to commensurability. And a key example is that if Y is a locally finite graph and we have an isometric action of a group on Y, then the stabilizer of a vertex is a coarse stabilizer of the action. So what this really, and this gives the one implies two direction in the definition of discretizability. So this is really just a reformulation of saying that you can, there's some nice subgroup which has the properties you'd expect of the stabilizer of a vertex if you had an action on a locally finite graph. And going forward, this coarse stabilizer is really the property that we want, the property we want to use that will allow us to prove things about discretizable spaces. And this is very closely related to the notion of an almost normal, also called commensurated subgroup. So a subgroup is said to be almost normal or commensurated, and it's denoted by this squiggly triangle symbol if every conjugate of H is commensurable to H. So clearly, if H is normal, then every conjugate of H is equal to H. Here's an example of a group containing a subgroup that's almost normal but not normal. So the Baumstock-Solitar group, BS12. This is an Hn extension of the infinite cyclic subgroup generated by A with stable letter T. And this subgroup here, this infinite cyclic subgroup, is easily seen to be almost normal but not normal, and it's not even virtually normal. And more generally, if we have a group acting on the locally finite graph, then the stabilizer vertex is an almost normal subgroup. So we have lots of examples. And if we have an almost normal subgroup, there may not be a quotient group, but there's a quotient space which roughly has all the geometry you might expect from the KD graph or word metric of a quotient group if the group were to exist, except the group is only, there may not be a quotient group. So if we have a group containing an almost normal subgroup H, which is finitely generated relative to that subgroup, i.e. there's some finite symmetric set such that H union that set generates the group, then there's a notion of a quotient space, which is, as a set, it's a set of left H cosets, and it's equipped with the relative word metric. So the distance between cosets GH and KH is the least n, such that G inverse K can be written in this way. And this is exactly what you'd expect. So if H is actually normal, then this is just the word metric on the quotient group with respect to S. And it has the properties you might expect from the word metric of a group. So it's a proper discrete metric. It's quasi-geodesic. It sort of looks like a geodesic metric space if you fill in the holes, if you connect the dots. and it's well defined up to quasi-isometry. So it doesn't matter what relative generating set you pick, you'll get the same metric up to quasi-isometry. And going back to the previous example, the Bam-Plug-Solitar group, BS12, with the almost normal subgroup generated by A, we see that the quotient space, G over H, is essentially the Basset tree. And you can see this very explicitly if you identify vertices of the Basset tree with cosets of this H. The distance between things in the Basset tree is just the distance in the quotient space with this relative word metric. Okay, so we've set up some terminology. We know what almost normal subgroup in a quotient space is, and we now have this very useful generalization of the Milnor-Schwarz lemma. So if we have a co-bounded quasi-action of a group on X with coarse stabilizer H, then the following things hold. Firstly, G is finitely generated relative to H. Then H is an almost normal subgroup of G. And furthermore, the quasi-action of G on X can be quasi-conjugated to the isometric action of G on this left coset space. So you really, once you have a quasi-action with a coarse stabilizer, all of the geometry of this quasi-action can be encapsulated in the group G and the subgroup H. And you can sort of see all of the geometry inside the group just by looking at this coset space. And my corollary of this is that if we have two quasi-actions of G on X and G on Y, which are co-bounded, and they have coarse stabilizers H and K, then the two quasi-actions are quasi-conjugate if and only if the subgroups are commensurable. So this, converts this geometric question, finding some quasi-isometry between X and Y, into something very concrete, algebraic, just deciding whether these subgroups H and K are commensurable. So it's really just converting this geometric stuff into some algebraic language, which makes our life easier. And another way of, another interpretation or another geometric consequences of having an almost normal subgroup is if the ambient group G is finitely generated and it contains an almost normal subgroup H, then you can think of the whole group as being a coarse bundle. I'm not going to define exactly what that means, but I'll give a picture in a minute, over the quotient space where fibers correspond to left H cosets. So going back to the example of the Bam-Plug-Solitar group with the almost normal subgroup H, what I've got here is a picture of the Cayley complex of the group, and you can see these squares with 5 sides correspond to conjugates of the relation. And these horizontal red lines are precisely cosets of this subgroup H. And the idea is you can see the quotient space G over H inside this by looking at the horizontal red lines and looking at the Hausdorff distance between them. And that gives you the quotient space up to quasi-isometry. And if we collapse all of these horizontal red lines to points, we just get the quotient space here. We don't really need this picture, but it helps understand what's going on in some later points in the talk. And this sort of picture was used either implicitly or explicitly in various Qri rigidity results, work of Faber-Moshe, White, Moshe-Segev White, and Eskin, Fisher and White. So far, I haven't yet given you any interesting examples of discretizable spaces other than trees, Moshe-Segev and White. But here we have, we can see how ubiquitous a discretizable space is. So if we have a finitely generated non-elementary hyperbolic group, i.e. just a hyperbolic group that's not finite and not two-ended, then it's either a uniform lattice in a rank 1 symmetric space, and quasi-actions on these are fairly well understood. This was building on work of Sullivan and Tukia and others from the, it was completed by the mid-90s. And if we're not in this specific case, where we understand the geometry very well, then we're discretizable. We're the generic case, generic hyperbolic group that's not of this very specific classical form, a lattice in a rank 1 symmetric space, is discretizable. That means that every quasi-action, co-bounded quasi-action, can be quasi-conjugated to an action on the locally finite graph. And I'll give a very brief outline of the proof. So using the geometry of this quasi-action, we give G the structure of a topological group, and you want things to be close in the topology of the group if they act similarly on X up to some uniform error. And a priori, this group won't be locally compact, but we can complete it to obtain a nice locally compact group G hat. And this is based on ideas due to Kevin White. And then we can apply some structure theorems for locally compact groups to deduce that essentially this group G hat is either totally disconnected or is a Lie group. And that corresponds to either this case, the group is a lattice in a rank 1 symmetric space, or it's discretizable. And this phenomenon isn't just the case of hyperbolic groups, it holds much more generally. So for groups of cohomological dimension 2, if we have a finely presented group of virtual cohomological dimension 2, then we have a trichotomy. It's either a surface group or virtually a surface group. By which I mean it's the fundamental group of a closed surface of non-positive Euler characteristic. What I call the mixed case, which is where the group is a generalized Banach-Solitar group. And you can see this is mixed. If I go back to the picture, this picture here, the reason why I call it mixed is because we have a continuous direction on the horizontal lines here, and you can translate by any real number in this direction. And we have a discrete direction on the tree factor here. So topologically, this looks like a tree times R, and we have continuous type behavior from the R direction and discrete behavior from the tree direction. So that's why I call these mixed. And if we're not one of these specific cases, again, the geometry of these has been studied and fairly well understood. The generic case, the group is discretizable. And the proof of this is very different to the previous theorem about hyperbolic groups. This uses the structure of the second cohomology module and results of Farrell and later Kleiner, and theory of JSJ decompositions of groups. One nice corollary of this is that in the generic case, the case where gamma is discretizable, every locally compact group that contains gamma as a uniform lattice is compact by totally disconnected. And this is sort of a fairly classical question to understand what possible locally compact groups can contain a countable group as a uniform lattice, and this provides a structure theory for that question.
Alex, you have 5 more minutes.
5 minutes, great, okay. So I can now go back to my original theorem that I stated at the beginning. So if we have a finely generated group quasi-isometric to a Z-bar hyperbolic group, then it's also Z-bar hyperbolic. So suppose we have some group which is Z-bar hyperbolic, because the automorphism group of Z is finite, it's order 2. We pass to a finite index subgroup such that the group is central. And then there's a result of Gersten, which says that if we have a central extension of a hyperbolic group, then it's quasi-isometric to a product of Z with the quotient Q. This uses bounded cohomology for hyperbolic groups. The result of Kapovich, Kleiner, and Lieb that I mentioned at the beginning says that if we have a group G prime quasi-isometric to G, then G prime quasi-acts on Q. And in the case where Q is not discretizable, when it's a uniform lattice in a rank 1 symmetric space, Kleiner and Lieb proved this in 2001, I think. And the argument is that it actually involves some work. It's not just an application of understanding quasi-actions on rank-1 symmetric spaces. But actually, if Q is discretizable, the example is easier. There's actually very little work you have to do, because you have a coarse stabilizer of the quasi-action of G prime on Q. And this coarse stabilizer is two-ended. That's not too hard to show. And so you can assume it's infinite cyclic. And because this subgroup H is almost normal, we have a homomorphism to the abstract commensurator of it, which is Q. And because the group is undistorted, the image of this map is contained in 1 minus 1. And so the group is, and so that means we pass to some finite index subgroup of H, and we get that G prime normalizes that subgroup. And we can actually generalize this to more general substantial extensions for higher rank free Abelian groups. So if the group is residually finite, then we get the result we expect. Any group Qi, a residually finite group quasi-isometric to a central extension is also a central extension. And brief note on why residual finiteness is used. It's to do with subgroup separability and the fact that if we have a separable subgroup, then if H is a separable almost normal subgroup, then it's commensurable to some normal subgroup. And if we drop the residually finiteness hypothesis, we get the same sort of theorem, except the subgroup is normal, is almost normal and not necessarily normal. But we still have a map from G to On to the group of orthogonal n-by-n matrices. And I should just say there are examples which are sort of counterexamples to this theorem if you drop the residually finiteness hypothesis. They're groups which are quasi-isometric to Z times F2, but have no normal Z squared subgroup. So the residually finiteness hypothesis is needed, but even if you drop that, you still have some information. And I say very briefly that this fits into sort of a program I've been working on, which is seeing more general situations when normal, almost normal subgroups are preserved by quasi-isometries in the following sense. And I'll just say that there are several examples that are already known in classical Qi rigidity results. And I'm working on generalizing them to more cases. But I think it's quite an interesting question. It hasn't been, there aren't too many positive results in the literature. Thank you very much. Any questions?
Any questions to the speaker?
Is there any analog in higher dimensions?
So there's a slightly more technical, you mean the cohomological dimension 2 condition? You mean? Oh.
No, but even though, well, you use the solution for Hilbert Free problem, but this you can use also in higher dimensions, right?
Yeah, I mean, it's a different...
You always assume that...
No, so the hyperbolic group theorem applies for any dimensions, and the cohomological dimension 2 one doesn't use Hilbert's fifth problem. It uses a different technology, and you can generalize it to higher dimensions, but you need to assume that the second cohomology H2GZG is non-trivial, and then you do get a generalization. So
the same type of generalization. Can I? Would that record it? It's so also either a lattice or discretizable.
I mean, for this theorem or for the previous one?
No, I can't hear.
There's this theorem which applies to hyperbolic groups in any dimension, and then there's this theorem here which is just for cohomological dimension 2. And I guess I don't really have an understanding of what the mixed case might be. So I have lots of sufficient conditions for discretizability, but I don't have a full understanding of the generic, I don't have a full understanding of what the continuous case and the mixed case would be. And there are various tools that you need for, there's a characterization of surface groups by Kleiner and by Bowditch in terms of cohomology, which doesn't exist in higher dimensions. So I wouldn't be able to get results that this strong, but I do get sufficient conditions that give you discretizability. Does that answer the question?
No, okay.
Other questions?
No, I guess what I meant,
Oh.
One, in higher rank, is there anything one can say in higher rank? I said higher dimension, but rank.
Oh, sorry, you mean like for not hyperbolic? Oh, I mean, in general, I think it would be very hard just because, yeah, I mean, I think you'd need some sort of coarse negative curvature to apply the same methods of proof that I don't know. I mean, I don't know if you drop hyperbolic here, I don't know what sort of theorem to expect, really.
Wasn't clear. Okay, never mind.
Okay, I suggest we take now the last 7 minutes for a break, and we meet at 3:35. Thank you, Alex. גיל, את מוכנה? גיל? היי גיל.
היי אורי. היי everybody.
נראה לי שאנחנו נתחיל, לא?
יאללה. So,
יאללה.
hi everybody.
רגע, אני צריך להציג אותך.
תציג אותי בבקשה.
Okay, so we're continuing. Our third speaker for this session is Gil Gofer from Weizmann, and she will tell us on generation and invariable generation and Weigold's conjecture.
Just a second. Okay, yeah, so hi, thank you for coming, and thank you, Nir and Chloe, for inviting me. I will tell you about invariable generation and the conjecture of Weigold. This is a joint work with Nir Lazarovich, and I will also mention Ashot Minasyan, that somehow independently, almost at the same time, published a similar result. Yeah, so I'm going to talk about invariable generation of groups. So let's see what it means. Just does anyone know how can I make the video disappear so that it does not block all my view?
We can see the presentation.
Okay, better. I remember most of what is there. So okay, so let S be a subset of G, and we're going to say that S invariably generates G if for any choice of conjugates of elements in S, the new set S prime, so that's the set of conjugates, also generate G. So it doesn't mean that I conjugate all elements of S by the same element, but I just conjugate each one of them independently. So I take a set S, I conjugate each one of the elements, I get a new set, it is called S prime. And then the question I'm asking is whether this S prime is generating or not, the entire group. If for any choice of conjugate it is generating, then I would say it invariably generates G. And then the group G is called IG, so this IG stands for invariably generated if choosing this set S to be G itself, so the entire group, this subset, the full subset, invariably generates G. So I take my entire group G, I conjugate each element separately by something, independently, I get a new subset S prime, then I ask, does this set always generate G? If so, then my group is called invariable generated. So if this can also happen that I can take this set S to be a proper subset and still it will work, so it will take S to be a finite subset, so I can take a finite subset that no matter how you conjugate it, it still generates the entire group. Then I will say that that G is finitely invariably generated. So that's Fig. The F is for finitely. So let's see some basic examples. So the most basic example would be an abelian group. So more generally, I would say that the intuition here is that this independent conjugation that you do cannot destroy too much your set. So it will not destroy it that much that it will become non-generating. So when your group is abelian, obviously S prime is going to be the same set S as you started with. And then if you started with the entire group, of course, it will still be generating. Second, less obvious example is finite groups. So every finite group is IG. So it's not very obvious to see, but it's you can do like a counting argument. and check that no matter how, if you take conjugates of all elements in the group, it cannot be contained in a proper subgroup. It is always generating the entire group. So that's the second example. Let's view one non-example. So a non-example would be GLNC, and the reason is the following. So let's say, so I take as S, I take the entire group, so that's GLNC. And now I independently conjugate the elements. I claim that I can conjugate all elements inside a proper subgroup. So inside a proper subgroup, what can this subgroup be? So you may guess that this is the upper triangular matrices. So I can replace each element in the set S, which is all of the group, by its Jordan form. So then it's a upper triangular. And obviously, if all of S prime is contained in a proper subgroup, then I cannot expect that S prime will generate G. So then in this case, since S prime is contained in a proper subgroup, then we get that this group is non-IG. So, and this example will somehow motivate me in giving an equivalent definition that I will present in a minute. So, so the reason I want to say that the reason for GLNC to not being IG is because it does have a proper subgroup which intersect all conjugacy classes. So it's a proper subgroup that all elements can be conjugated into. So that's exactly the second definition. The equivalent definition would say that that a group is IG if and only if it does not have such proper subgroup. So a group is IG, that's an equivalent definition, if whenever you have a proper subgroup, it cannot intersect all conjugacy classes. So its conjugates do not cover the entire group G. By the way, a subgroup like that, a subgroup which is which does intersect every conjugacy class, is called conjugacy complete. So if I want to say in words this second definition, I would say that a proper subgroup cannot be conjugacy complete. The Borel subgroup in GLNC is a conjugacy complete subgroup. If you don't have such, then you are IG. Okay, let me just view one last equivalent definition, which is a bit more dynamical. So instead of saying every proper subgroup, like here, I want to think of every proper subgroup as a transitive action of G, which is non-trivial. So it's on a space of more than 1 point. So G is called IG for every non-trivial transitive action. So you see this transitive action is like saying that H is proper. So whenever G acts transitively, so you see that here I want that there will be an element that is not contained in any of the conjugates of H. Now we know that when G acts like this on the coset space, then we know that H is exactly the stabilizer of the trivial coset, right? And each conjugate of H is nothing but the stabilizer of some other coset. So saying that the conjugates of H do not cover G, this is exactly like saying that there exists an element in G, there exists an element in G acting with no fixed point. So it does not belong to any of the stabilizers. This is like this condition here is that there exists an element acting with no fixed points. The third definition, if I want to state it in words, I would say that this is a transitive group acting with fixed points free permutation. So there is always a permutation which is fixed point free. The third definition was actually the original definition that Wiggold, the guy from the title of the presentation, used. So he called these groups transitive groups with fixed points free permutations. Before I go on, there are questions. Like you can interrupt me during the lecture. Okay. So these are the three definitions. And first thing to ask, so Wiggold, when he started studying this class of IG groups, he was checking like, what are the properties of the class? Which operations can you do and still stay in the class of IG groups? So first he observed that the class is closed under extensions. So if you extend an IG group by an IG group, you get another IG group. And actually something slightly stronger holds. So that's what's written here. So if H is a finite index subgroup, so you see it doesn't even need to be normal, it is just any finite index subgroup. Then if H is IG, then the ambient group G must also be IG. And if H is Fig, then G must also be Fig. Let me sketch briefly the proof of the first statement, and the second the second part is somehow the same, very similar. So what we do is we are going to pass to a normal subgroup. So whenever you have a subgroup G, you can consider its normal core. So what is the normal core? So the normal core of H is just the intersection of all of its conjugates. And this will already be normal inside G. And if H to begin with was finite index, then this is also this would also be a finite index subgroup. It's finite intersection of finite index subgroups. So we know that in our case, this normal core is going to be a finite index normal subgroup. And now we are going to observe. So we don't know that N itself is IG. This we don't know, but we do know that G mod N is IG, because N is a finite index, and so G mod N is a finite group. So we're going to show that G is invariably generated using the third definition, the dynamical definition. So what do we need to do? We suppose that we let G act transitively on some space, which is larger than 1 point. And now we want to show that there exists an element acting without fixed points. Okay, so now observe that since N is normal, you know that G mod N, the quotient group, acts on the space of N orbits, acts on the space X mod N. And now there are two options. Either this action is non-trivial. So what do I mean by non-trivial? I mean that either this action, this space of orbits has more than one element. In this case, I can use the fact that G mod N is finite, and therefore it's IG. And now using the third definition, I know that I can definitely find an element acting without fixed points on the set of orbits. But you know, if it has no fixed points in the set of orbits, then obviously it has no fixed points on X. And then this is so then I got I found the element I want. So this is one option. Second option would be that this is the trivial space. So it is the 1 point space. So if there is only one N orbit, this would say that N itself was acting transitively on the space X. In case N was acting trivially, then obviously in case N was acting transitively, then obviously H was acting transitively on X. And if H acts transitively on X, then since H was IG. This is by assumption, right? This is this assumption. If H acts transitively on X, by the definition of IG, by the third definition, I know that there exists some element H in H, which is fixed points free. And this element is in particular in G. So this is the required element. So you see that it's somehow almost direct to see that this behavior being IG is going upward. So from a finite index subgroup to the ambient group. It is also pretty direct to see that it passes to quotients. And then the next natural question is to ask, and this is James Wiggold. So he was asking, what about the other direction? So what do I mean by that? So if I knew that the group G is IG, could I deduce that its finite index subgroup H is IG as well? So on the beginning, Wiggold was asking this question without even assuming finite index. He was just asking this for a general subgroup. So if you have an IG group, does every subgroup need to be IG as well? So for the obvious examples that we saw, so we saw that like abelian groups are IG, obviously their subgroups are IG. We saw that finite groups are IG, obviously their subgroups are also finite. So it took some time to figure out an example which doesn't follow that, but we will see this in a minute. Later on, so Cantor, Lubotsky, and Shalev raised this question again, the first question, and also added the second one. If I know that G is finitely invariable generated, and I know that H is finite index, does it follow that that H is also FIG? So Wiggold himself did not use the term FIG. I think it's Cantor, Lubotsky, Shalev who stated this definition. You know, I think Alex is here, can correct me if I'm wrong. I think it's their terminology, FIG. So we are wondering about the other direction. So this question was raised in '76 by Wiggold and repeated in 2014 by Cantor, Lubotsky, and Shalev. Okay. So 1 year later, in '77, Wiggold himself found an example for an IG group which admits an infinite index non-IG subgroup. So this is, it makes this assumption, this finite index assumption, necessary for the conjecture, right? So, so this is an IG group with a non-IG infinite index subgroup. I think, okay, I will just really briefly sketch it with no details so that I don't run out of time. So he took the set omega, so that's a countable set made out of 3 copies of the natural numbers. And here are 2 chosen elements in the symmetries of omega. And we consider the subgroup generated by these 2 elements. It's a subgroup of sim omega. And it is not very hard to show that this subgroup is invariably generated. So one can actually follow the definition step by step, assume that you had, assume toward contradiction, you had a proper subgroup, blah, 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 and you get that. But this subgroup admits a proper subgroup, so that's the commutator subgroup. And it comes out that the commutator subgroup consists only of finitary permutations. So one can do the calculation and find out that the commutator comes out to be such things. So for example, the commutator of A and B comes out to be this transposition. And other commutators as well. And then elements in the commutator subgroup here in P prime are all finite products of chilufim, and so I know that they are all finitary permutations. Why this implies that this group is IG, is non-IG. So this group acts on omega, and it's also not hard to check that this action is transitive. But being a finitary permutation, this is by definition means that you are finitely supported. And so if it's finitely supported, definitely it's fixed as a point. So P prime does not contain any element which acts without fixed points. So using the third definition, this is a non-IG group. So that's Wiggold's construction showing that the property does not pass to subgroups. Okay, but the question still remained open for finite index subgroups. And for finite index subgroup, it was still open. Okay, so what we did is we constructed a group G with a finite index subgroup H. So it's not only finite, it's actually index 2 subgroup, such that H is non-IG and G is IG. So just before I sketch you the construction, let me just say that this gives a negative answer to both questions, since okay, wait, I'll come back to that. So we assume that the group G is FIG. So FIG is the stronger among both. So it's like saying that our group G is FIG, so in particular it is IG. So we assume both of these assumptions, and we get that our subgroup H is non-IG. So it's not IG, so obviously it's not FIG. So we get that both that H is not IG and not FIG. So this construction gives these two negative answers to Wiggold and Cantor-Lubotsky-Shalev's question. So let me sketch briefly the construction. Okay, so what we do is we produce a finitely generated non-IG group H, and such that it admits an involution. So this is just an order 2 automorphism. And we mark some specific element, this is X, that will have this weird property that we think of this property as each conjugate. So X is not invariably generating. So it's not that every conjugate of X generates the group. This does not hold. But each conjugate of X phi generates the group. So if you take a conjugate of X together with its phi image, they generate the group. So we think of it as saying that X is, let's say, phi invariably generates H. So together with its phi image, every conjugate of X generates the group. And then we set G to be this group generated by X and phi. So it's like the semi-direct product, and phi acts as it was defined as an involution. Okay. So just let me sketch why this construction actually gives the requirements here as above. So it's obvious because phi is of order 2 that this H sits inside G as a index 2 subgroup, and also H is non-IG by construction. So we construct it to be non-IG group. And now we're going to claim that G is actually such G. If we have these properties, we claim that such G is indeed FIG by these two elements. Fig, so I need to give you a finite subset. This is going to be these two elements, x and phi. And I claim, what does it mean to say that G is Fig? It means that I want to claim that every two conjugates, every conjugate of x and conjugate of phi together generates the full group.
Gil, you have five more minutes.
Okay, toda. So I take arbitrary conjugates of x and phi, and I want to claim that that this k equals the entire group G. This would finish the proof. So let me just briefly sketch that. So without a lot of generality, I can assume that phi itself is inside k. The reason is that if I can conjugate the entire k, I can replace k by a conjugate of it. And then if I show that this conjugate is the entire group, then obviously k is the entire group. So without loss of generality, I can ignore this conjugation of phi by replacing G with another element. Now, since our group G is generated by H and phi, then I can write G as follows. H times phi may be to the power of 0, right? The form of G may either be just H or H phi. Now, since I assume that phi is in K and X conjugated by G is in K, then by conjugating by phi again, I get that also X conjugated by H is in K. And since phi is in K, then also phi of this is in K. And now, by assumption, so the idea of the construction was to make X have this property that for any age, these two things generate the entire age. So I know that if I have this and this inside K, then the entire age must be contained in K. And then since G is these two elements, is generated by H and phi, then if I contain H and I contain phi, then I contain the entire group G. Okay, I guess I have 2 more minutes just to tell you maybe. So this is like a list of 3 properties. I hope I managed to convince you that these 2 properties actually give us what we want. But how do I get a group with these properties? So the idea is to to start by a free group over, we started by a free group with 4 generation and just adding more and more relations to make these properties to make these properties happen inductively. So we enumerate all elements in F and just step by step we force these properties to happen. So for example, if we want that for every conjugate of X, this will be generating the entire group H. I'm looking now at the second property. I'm gonna force all these 4 elements to belong, by adding relations, to belong to this subgroup generated by this conjugate for every element. So I'm just going through all conjugates of X, and to each one of the conjugate, I just force these 4 elements, these 4 generating elements, be inside these generated groups. So this is done by inductively adding relations. We add these relations, and during the process, we want to make sure that our group is still not degenerated, and we still have freedom to keep adding relations on the next step. In the end, we will set our group H to be what is generated by these 4 elements with all the added relations that we added on the way to make these properties being satisfied. Okay, yeah, so that's the construction. So now we know that the IG property does not pass to finite index subgroup, and same for FIG. Okay, yeah, that's it. So thank you for listening.
Thank you, Gil, for the talk. Any questions?
מישהו מנגן בחלילית מאוד יפה.
לא פה. Okay, so if there are no questions, then we have, let's thank Gil again, and we have 9 minutes of break.
I just want to check if everything is all right with the sound. Can you hear me? And is it okay?
Yes,
Yes, I can hear you.
Yeah, perfect.
Maria,
Mm-hmm.
how do you pronounce your last name?
Like in Russian, it's Gerasimova, but you can pronounce it like Gerasimova as you want.
I will try.
Yeah, it doesn't matter really. So.
Okay. Okay, we should start soon. Let's give people a minute.
I know that there are some people who have already heard this talk, so I'm sorry for repeating, but well.
Okay, so welcome back, everyone. Our final speaker for this session is Maria Gerasimova.
Thank you.
From Bar-Ilan University, and she will tell us about isoperimetry, Littlewood functions, and unitarizability of groups.
Thank you for the introduction. I'm very happy to speak here, and I will speak about unitizability of group in general. So, but before I will give you some definitions, let me give you some basic example or some motivation why do we care about this. So, if you have a finite group, in my talk I will be mostly interested in infinite groups. So, just for this moment, let us assume that gamma is a finite group. And let us assume that we have some representation of gamma on a Hilbert space H. Then, so if I will just define a mu scalar product like this, so I will average over my group gamma, then I can make my representation phi to be unitary. That's the basic and very classical result, I guess. So we just average, and this is a very nice result, and this is our, like, in some sense, our motivation. But I should say that if you're passing from finite groups to infinite groups, this is not always the case. For example, we can consider some very nice infinite groups, like, for example, you can take Z and try to do something like this, but we can define a representation which is not, which we're not possible to conjugate to a unitary one. So, for example, let me define phi in the following formula, by the following formula, and I claim that the reason why we cannot conjugate it to the unitary one is such that the supremum of all group elements of the norms is equal to infinity. So if we want to try to do something the same for infinite groups, we should be careful. And now I can explain why do I need the following definition. So first of all, in my talk, I will always assume that gamma is a discrete group, and let me do the same. So I will say that my representation is uniformly bounded if the following holds. So just exactly what I wanted, not to consider all groups and all not to consider all representation, but I would like to focus on some class, the class of uniformly bounded representations, and this is very natural definition in some sense. And what I want to say that the second definition which we want to define is definition of unitarizable representation. So I will say that my representation is unitarizable. Oh, I'm sorry, unitarizable if there exists an equivalent gamma invariant in a product on H. So it really means that I can conjugate. It is really equivalent to the fact that I can conjugate my representation to be unitary. And let me write it like this. So I will say that phi is unitarizable if there exists some operator S, such that if I conjugate my representation, it will be unitary operator for any G in gamma. And it is not very difficult to see that if you have an unitarizable representation, then it will be uniformly bounded. So I claim that we really have some inclusion like this. And the bound will be something like the norm of S multiplied with the norm of S minus 1. So it is quite easy, but not the other way around. And I will define it like a property. I will say that I have if I have a group gamma, I will say that this group is called unitarizable if any uniformly bounded representation is unitarizable. So one way it is always true, and other way we will focus on groups like this. So, and the most natural question, of course, what can we produce some examples, maybe or non-examples, what can we say? So first of all, let me mention that we already know that finite groups are unitarizable, so I will write that finite groups are here, so they are unitarizable. And later it was proven that actually the group of integers, so for the first result, I think, and the second one, it was like the group of integers, if I take just Z, it is also unitarizable. But the question is still open, so maybe all groups are unitarizable, and this is not an interesting class of groups, but no, and later I will give you some non-examples. But before passing to non-examples, let me observe that all these groups, like finite groups and groups of integers, is like representative of a wide class of group, which we call amenable groups. There are plenty of definition of amenability, and I think you know a lot of them. So, but I will just remind you two of them, which will be like the most relevant to what in our case. A discrete group gamma is called amenable if, for example, for for any finite set f and any epsilon bigger than 0, there exists a finite set u such that the following condition holds. So this is called a Kernel Condition. Maybe we can focus on this definition. And what was proven further, it was proven by Day and Dixme independently. Let me write like this. They actually proved that amenable groups are also intrisable. So amenable groups are intrisable. And actually, what they used for the proof that like the fact that in amenable groups you can in some sense take the average, and then this result actually led to the question which now is called the Dixmere's problem. I'm not sure that it was really a Dixmere conjecture, but it was this question which he asked. So are unitizable groups amenable? And this conjecture is open, I think, for more than 60 years already. We now have some partial results, but the question is still open, so it's still unknown. What we know that free groups are not unitizable, and we also know that if I have a free subgroup inside my group, then this group is also not unitizable. But I think, as you all know, that unfortunately not. This looks very nice because we know that free groups are also not amenable, but unfortunately not. It is well known that not every non-amenable group contains a free subgroup inside, and there are a lot of non-amenable groups without free subgroups. They can be also torsion, for example, and they can be very, very complicated. But it's also known that, for example, for some torsion groups, we also have some examples, and like the famous torsion group, which is not amenable, it is Burnside groups. I will come to it later when we will speak about applications, but let me just mention this now, that it was proven by Nicolas Monod and Ozawa that Burnside groups of large exponents are not unitizable. By large exponents, I mean that pi should be bigger than 665, and maybe I need also that m is bigger or equal than 2, and some pi should be odd, something like this. But in the moment it's not very important, but still, so it's we don't have any counterexamples in these families of groups. We know that they are not amenable, but they are also not unitizable, unfortunately. And this makes this question very hard in some sense, because for non-amenable groups which do not have free subgroups, it's very complicated to analyze them, in the sense that they are usually constructed as the monster groups, so they satisfy some specific properties, but you cannot say a lot of things in general. And there were basically two different approaches, one due to Bézier, who uses operator spaces, and another due to Monod and Ozawa, who uses, I think, mostly bounded cosmologies. But the fact was that, like, if you add some additional condition, for example, Bézier this condition that if your group gamma is unitizable and you can find any unitarizer S with some specific properties, like that the norm of S and the norm of S minus 1 will be less than some constant or whatever. But I just mean that it's not very important for my talk, but I just mean that if you add some condition, then you can show that unitizability implies amenability. And also for this approach, so they prove that if some risk product with some infinite abelian group is unitizable, then the group is amenable. So I mean that if the gap between unitizability and amenability really exists, it should be very narrow. But what I'm going to talk about today is a different approach related to the space of Littlewood functions. This space is, it could be, I don't know, the definition could be not very clear if you see it for the first time. So this is the space of all functions on my group gamma, and these functions should admit decomposition in the following way. So for any S and T in my group gamma, I can decompose the value of the f of its product as the sum of two functions of two variables. And I also need something like this. So I need, if I take supremum or all S and sum over T, this sum will be, this supremum will be less than infinity, and other way around for if I take the supremum over T. So this is some condition which I want to be satisfied. And I will also define the norm on this space of function. So it will be a norm, it will be a Banach space actually. So I define the norm in the following way. So it will be just the infimum over all such compositions. Maybe I should write it like this. So over all the compositions of exactly these supremums. So let it be C1, let it be C2, then it's like C1 plus C2. So of course I think you would like to have some examples of functions which belong to the Littlewood function space, but I should say that it's not very trivial to find such examples. But what I can say tell you that L1 of gamma is a subspace of T1 of gamma, and T1 of gamma is a subspace of L infinity of gamma. So something like this. We know this is not very hard. But what is interesting about this space, and why do we actually need this space? Because this space is related to amenability and also to increasability. What I mean is, I want to mention two results. I think a basic point of a start point for this research. The first result is due to Wysochansky, and he proved that amenability can be characterized actually using these spaces, and we can say that our group gamma is amenable if and only if I wrote already that L1 of gamma is a subspace of T1 of gamma, and if I have that T1 of gamma is a subspace of L1 of gamma, so they are the same, then this is really a characterization of amenability. And this is not the end. And another result, which is more relevant for us, this is something about increasability. We know that if gamma is unitizable, then T1 of gamma is a subspace of L2 of gamma. But I should tell you that you should be careful, because here we don't have any characterization. We know only one way. So if gamma is unitizable, then something false. But other way around, we have no idea what is happening. So, but still, it gives us like some connection between amenability and increasability. And what we managed to prove first, and what really prompted this research, it was the results due to me, Dominique Gruber, Nicolas Manon, and Andreas Stone, that for any non-amenable group, actually, you can find some phi bigger than 1, so that T1 of gamma is not contained in LP of gamma, something like this. So, and you can actually define the Littlewood exponent in the following way. We will say that this is just the infimum over all p, so that T1 of gamma is a subset of LP of gamma, subspace, I'm sorry. So this is some invariant in some sense, analytical invariant, which really relates to some some Banach spaces. And let me reformulate what I told you before in these terms. So we know that Littlewood exponent is equal to 0 if and only if gamma is finite. And this is the last moment in my talk when I'm interested in finite groups. In all what I'm going to say, I will assume that gamma is infinite. But still, we also know that due to our result and result of Wysochansky, actually, that Littlewood exponent is equal to 1 if and only if gamma is infinite amenable group. We know that, but only one way, that if gamma is unitizable, then Littlewood exponent is less or equal than 2. And we also know that for free groups, which are the most common example of not unitizable groups and not amenable groups, we know that Littlewood exponent is equal to infinity, not only for free groups, but if you have a free subgroup inside. So let me draw a picture. I think it's very nice. Here we have 0, and here we have finite groups. Here we have 1, and here we have amenable groups. Infinite amenable, of course, infinite amenable. So if amenability and unitizability is not the same, we have unitizable groups somewhere here, unitizable groups. But I should repeat again that non-unitizable groups can also can also have Littlewood exponent between 1 and 2, so we don't know. And here we have free groups let me write groups with 3 subgroups. It will be groups with 3 subgroups. But maybe it's not very clear intuitively, but when you look on the proof, how people really prove that Littlewood exponent, so how can we prove that Littlewood exponent is equal to infinity if you have a 3 subgroup? It looks like that this is a very strong property, and maybe Littlewood exponent, which is equal to infinity, should be somehow a characterization, but unfortunately no. And we proved that there exists finitely generated torsion groups such that Littlewood exponent is equal to infinity. So I should write here like strange torsion groups because you can construct many of them. And so unfortunately it was too optimistic. But like if you look on the picture, you will see that the main equation is, can we say something more? Because now it looks like that maybe Littlewood exponent can take only values. Is it true that it can take only values 0, 1, and infinity, or maybe in some sense it is trivial and not very interesting to study? But no, I would like to just firstly to observe how it behaves under taking some group operations, and then I will explain you why it is interesting. So first of all, if I have a subgroup, then the Littlewood exponent behaves like this. If I have a quotient group, then we also have an inequality, and moreover, it's easy, follows easy from the second part. So if I have a finite index subgroup, then the Littlewood exponent of the group and of this subgroup coincide. And I think what is more important, actually, before I will pass to explanation of some geometry, of course, we need some examples. We need some non-trivial examples to show that Littlewood exponent is not trivial, but it's very difficult if you recall the definitions once again. So it's very difficult to work with the definition because we are taking infimum over all P, such that T1 of gamma is a subspace of LP of gamma. And it's not very clear how to construct groups using the definition, because usually for complicated groups you're not able to say anything about T1 of gamma, and so it's very hard to work with the definition. So we need some relation maybe to some geometry or to Kelly graphs, because with Kelly graphs we are more used to work, and it is very nice that such connection really exists. I will consider a finite symmetric set and consider Kelly graph with respect to this set. Here I'm not assuming that that S is generating. So, and just for simplicity, let me assume that for a moment that E is not neutral element is not inside the set, just to avoid loops. We can define a Qri constant, and it's well-known thing in geometric group theory. And but in my talk, I will be interested not exactly in Qri constant, but in something which is related to it. And I will define E of gamma S and call it like relative maximal average degree, where E of gamma S is just 1 minus Qri constant divided to the number of elements in S. So, or I can rewrite it as a supremum or all finite subsets, where I take number of edges inside F, multiply it by 2 and divide by the number of elements in F and number of elements in S. I will try to give you some intuition why we call it relative maximal average degree, but my invariant, which is related to Littlewood exponent, will be a little bit different. I will also, I want to pass from S, and I will define my invariant as the minus limit of the logarithm of this E of gamma S divided by the logarithm of the cardinality of S. It looks very strange, and I understand you. So, but maybe just to say something about that. For example, if you will look here, that on amenable groups, it is well known that Qri constant is equal to 0, and then this relative average degree is equal to 1 actually. So this will be just 0, and the Littlewood exponent for amenable groups is equal to 1. So if you just take this as an example, So maybe they satisfy some equation which really connects this invariant, which looks very strange, and the Littlewood exponent. And indeed, yes. So the connection is the following. So let me just skip this. And yeah, and maybe I'm sorry. I also need to say something about free groups. So that for free group, I know that it's not very strictly, but not very maybe a little bit sloppy. But just think about tree. And then, like, what is E of gamma S for a free group? It will be something like 1 divided to the cardinality of S. So this will be equal to 1. And just to give you some intuition, we are really trying to catch this power. Actually, well, this E of gamma is really some invariant which really tries to catch this power. So I claim that E of gamma S behaves like 1 divided to the cardinality of S to the power alpha, and we are trying to catch it alpha. And the connection between the Littlewood exponent and this eta of gamma is the following. So that for any group, we have the following equation. Eta of gamma is equal to 1 divided to 1 minus 1 divided to the Littlewood exponent. And it really gives us some opportunity to construct some groups, because of course, okay, I see that this invariant is still very complicated, because if you want something to hold, you really need to control some property for all finite symmetric sets. And maybe if I just give you some arbitrary group, it's not possible. But at least now you can try to construct some group. And this is what was done. Using the small constellation over hyperbolic groups, it was proven that we have such a group which has the Littlewood exponents between 1 and infinity. So if you recall my picture, we have something at 0, we have something at 1, we have something at infinity, and now we have something between 1 and infinity. Unfortunately, it is not very clear if it's really between 1 and 2 or between 2 and infinity, but at least it is some example which really shows that Littlewood exponent of gamma is not trivial, so it does not belong only to the set like this. And we have some complicated groups which have Littlewood exponent between 1 and infinity. And also, I should tell that I don't know if this group is unitizable or not. This group is very complicated, as I told you, because it does not have a free subgroup inside, and it is constructed as a limit in some sense, because you really need to control some property for all finite symmetric sets. How many time do I have? Just to okay.
6 more minutes.
Okay, so I would like also to tell some connections, but maybe some applications, but not too much of them, because I don't have enough time. Just let me say that there is also some connection with the spectral radius of the Markov operator, because for some groups it's maybe easier to control the spectral radius. And I can just define the invariant in the way like this. So I will just take again the minus limit, but I will take the logarithm of the spectral radius. And then we have the connection like this. But you do not have to try to recall all the inequalities, but just to say that sometimes when we know something about this spectral radius, we can say something about this R of gamma, and then maybe we can estimate Littlewood exponent for some groups. For example, it was done for Untitled groups. I already mentioned them, and this like the example of torsion groups, which are defined as the quotient of the free group on M generators, and like quotient by the normal subgroup generated by all piece powers. And I should say that these groups are also very complicated, because, for example, I know that for like if you take 2 generators and the exponent you choose exponent to be equal 5, it is not clear if this group is finite or infinite. So, but it's known for that for big big power. If I take big exponent, like as I told that already, that it should be bigger than 665, and then should be bigger or equal than 2, and p should be also odd, then you can estimate the Littlewood exponent. It is bigger than 3/2. Unfortunately, it is not what I really wanted, but still something. There is some conjecture that maybe it should be equal to infinity or maybe not. So there are two different conjectures, and unfortunately at the moment I don't know how to solve it. But still, and another, this I will skip. And another, I think, nice example is is some connection with L2 petty numbers, because it's also a very popular topic in geometric group theory. And so if you have no idea what is L2 petty number, let me just say that I will say that L2 petty number of gamma is bigger than 0 if and only if gamma is non-amenable, and there exists some map which like from gamma to gamma, which satisfies the following property, and this map should be unbounded, like if we have an unbounded cycle. And these groups are also, people think that people mostly think that this group should be somehow related maybe to negative curvature or something like this. So probably they all have 3 subgroups inside, so it's not clear. But what we can prove that that if I have a finite degenerated group and I assume that also it is residually finite and L2 petty number is bigger than 0, then little exponent is equal to infinity. So maybe it also gives us some examples. Unfortunately, only here at the end. So there are many other nice applications, but unfortunately I don't have enough time to explain all of them. But what I want to say maybe in the end that and what I was talking about, we were speaking only about Hilbert spaces, but you can also try to pass from Hilbert spaces to some other spaces, for example, to some other Banach spaces, like one class of spaces which is very natural in this direction, it is P spaces. So let me just recall that the Banach space is LP space if it is of the form like LP of x mu, where for some measure space x, and the P space is just LP space is just a space which is isometrically isomorphic to the quotient of a closed subspace of these LP spaces. Why do I like them? Because for P equal to 2, these spaces are exactly Hilbert spaces. So if we want to generalize increasability in some sense, maybe this is a nice, these spaces are nice candidates. Unfortunately, we cannot do exactly like in the case of Hilbert spaces, because I cannot say that my representation is parameterizable. For example, if I can conjugate, it's different, but I can still say that my I will say that gamma is parameterizable for any P space and every uniformly bounded representation there exists in U P norm, such that this representation becomes isometric with respect to this norm. And then we can prove that, for example, amenable groups are parameterizable for any phi bigger. I should write, I'm sorry, bigger than or equal than 1. And our friend free group, which is like the most common example for non-increasable group, it is also not parameterizable for any pi bigger than 1, something like this called. So the idea was that maybe there is some connection between the values of the Littlewood exponent and the and P for which our group is parameterizable, but unfortunately I'm not still there because there are some complicated problems related to some geometry of Banach spaces, which I don't understand, and there are some open conjectures, but still it would be the way to understand this Littlewood exponent better. And before I finish, I would like also to mention that I told that the strong negation of amenability is like the existence of a free subgroup, but usually when I say that something about strong negation, people ask about property T. So maybe very natural question, can we say something about property T groups? And unfortunately, it is open. So I think there are no results about the property T groups, but this will be very natural. So maybe if we think that amenability and increasability is the same, can we say that if increasable group, if property T group is increasable, then it should be finite. So, but it is completely open, and I have no idea how to do it. And yeah, so just to to say something about the theory itself. So I think I will finish here because I don't want, I think, to give more examples. I think it was still very complicated. I'm sorry if it was so fast.
Thank you, Maria.
I'm really sorry if it was too fast because I'm still not very used to give talks via Zoom. Yeah.
I followed. Any questions? If not, then let's thank the speaker again, and we now return to the main. Sorry? Yeah, you're trying to say something? Ah, no. Okay. That wasn't the question. So we return to the main event, right, Chloe? Am I right? And thank all the participants and all the speakers of the session.
Thank you. Thank you, Molly.
I think the main event starts at 5, if people want to.
5, okay. So we have 30 minutes to gather ourselves. Okay, see you there.
See you.